Recent events in the media have told us of a new breakthrough in fusion research, right? They've taken a single atom of deuterium and one of tritium and basically got them so excited that their internals, their neutrons and protons, started acting together. But here's the challenge. Here's the big challenge in this. Those neutrons and protons contain particles we don't understand yet. But we do understand. We see the outputs of these events every day when the sun rises. We see the outputs of these events, what is created from that. Now it's rather odd because the color white that the sun appears to be doesn't exist in science. Well, it does. We've put it together. We've constructed it from our explanation of the color white, a human explanation, a human take on it. But white is simply a whole lot of colors put together. That's a whole another amazing conversation to have about colors and what they are and mean and how you put them together. A good study would be the Pantone color scale and how it's applied. It's one of probably the most used behind the scenes color scales because it's an industry standard. Helps us paint cars the same color. All right, back to fusion. So they've managed to excite these particles enough for the components within the nucleus of an atom we commonly refer to, we understand as neutrons and protons, but there's more in there that we know. That's the work of CERN. That's their life study. So what teaches us about the outputs of a fusion reactor? Let's go to space. The Parker Solar Probe is telling us what the outputs of a fusion reactor are. It's heading towards taking another flyby sample, the closest in human history that our instruments, our technology has come to the sun. That's where we are. That is going to tell us what the output of a fusion reactor is, not these guesses and hems and haws. That's actual physical measurements by known, respected instruments of the output of a fusion reactor. What escapes the mass of the sun? The sun has no containment. Its containment is its own mass, its own gravity, keeping the particles close to itself. Yet some escape, and that's what Parker is measuring, those escaped particle emissions. It has physical measurement devices on it. So, it's too cold outside to play here, but that's the video. There's more to this. It should be discussed. What are the outputs when you take the guts of atoms and stir them all together? What's the actual equation for that? What are the stochastic odds of other particles escaping, other types of elements, other combinations of those subatomic particles in the nucleus of an atom? We could argue whether there were other atoms involved in that reaction. For in order for there to be no atoms, you have to have a perfect vacuum. An absolute vacuum. When it's all relative. So that help? That make it easier? Peace out, folks.